I'm going to let T be a transformation from R2 to R3, defined by T of x equal to AX, where A is given by this matrix here. If x is the vector negative 6, 4, I want to find T of x. So I want to be able to figure out what the output is. I'm given the input, and now I need to determine the output. We know that T of x is defined by A times x. So I have my matrix A, and I need to multiply it by my given vector x to determine the output. As we multiply this, I have 1 times negative 6 is negative 6, 6 times 4 is 24, and negative 6 plus 24 is 18. My second row, negative 6 times negative 3 is 18, 3 times 4 is 12, and 18 plus 12 is 30. My last row, negative 1 times negative 6 is 6, 0 times 4 is 0, and 6 plus 0 is 6. So now I have my solution. I have my output vector. I have my same transformation again, and this time I'm given a vector u equal to negative 4, negative 9, negative 2, and I want to find the x such that T of x is equal to u. Before, I had my input and I wanted to determine the output. This time I have the output and I want to determine the input. So I have this here. I want to know A times what is equal to this vector u. So I have AX equal to u. And this is our matrix equation. This is just a system of equations. So I need to get a matrix and row reduce. So let's scroll down a little bit so we have a little more space. I need my matrix A on the left. And then on the right, I have this vector u, the negative 4, negative 9, negative 2. And we want to row reduce this. And when we do, we get 1, 0, 2, 0, 1, negative 1, and 0, 0, 0. So that gives us our solution. We were looking for the x that gave this vector u as the output, and that vector is given by 2, negative 1. And we can double check. Multiply this matrix A times this vector x and show that you get negative 4, negative 9, negative 2. Once again, I have my same transformation that I was dealing with before. And this time I have this vector v, negative 4, negative 9, 1. And I want to determine if v is in the range of t. So I want to know, is there an x such that T of x is equal to v? And this is exactly what we did in the last problem. So we're going to set it up exactly like the last problem. We know we're going to have to row reduce. We have our matrix A on the left and our vector v on the right. And when we try to row reduce this, what we end up with is that there is no solution. This very last row gives us 0, 0 equal to 1, which is definitely not true. So it is not in the range. Since we have no solution, that means there is no input that would give this as an output. Now that we're a little more comfortable with transformations, let's look at what an actual linear transformation is. Let's suppose we have a transformation T going from Rn to Rm. We know x and y are in Rn, and C is a scalar, so we have two input vectors and a scalar. And we say it's a linear transformation if two things are true. The first, T of x plus y is equal to T of x plus T of y. I can break up my transformation over addition. And the second one, T times C of x is equal to C T of x. I can factor scalars in and out. Let's consider a transformation like the one we were dealing with earlier, T of x equal to AX. This is a matrix transformation since it's defined by a matrix. If we want to consider t of x plus y, well, by definition of our transformation, this would be a times x plus y. We had previously discussed that matrix multiplication does have a distributive property, so this is ax plus ay. Well, ax is the definition of t of x, and ay is the definition of t of y. On the other hand, if I want to look at t of cx, this would be a times cx. And once again, when we define matrix multiplication and scalar multiplication, we talked about how we can factor out scalars, multiply them first or second. So this would be c times t of x. So these matrix transformations are linear. And this is going to be a really nice property for us to have. So let's look at two other properties of linear transformations. My first property for a linear transformation, t of 0 is equal to 0. If you input the 0 vector, you will output the 0 vector. This is because if I have t of 0, well, that's the same thing as 0 times any vector. Since 0 times a vector is still 0 vector, I can factor out a scalar, and then 0 times anything is going to be the 0 vector. So I have that property holds true. My next one, t of cx plus dy is equal to ctx plus dty. So once again, this is a linear transformation. We know linear transformations can be broken up over addition by the basic property of a linear transformation. So now I have t of cx plus t of dy. We also know we can factor out scalars from linear transformations. So now I have c times t of x plus d times t of y, which gives me the final result.